Hi, so today's talk is about big news which is rocking the world of science since last week. The first ever picture taken of a black hole. And this picture taken is of a black hole which is there at the center of a galaxy called M87, Mathur 87. And the picture taken is of a black hole which is there at the center of this galaxy, this massive galaxy. So I'll talk a little bit about what is a black hole, and then we'll go into details about this black hole for which the image has been taken and how this image has been taken. So yeah, basically a black hole is formed by collapse of a star. The star remains in that state due to a balance of a force. Like there's an outward force which is acting because of the thermonuclear reaction which is happening in the black hole, that is creating an outward pressure or an outward force, and the gravitational pull is trying to collapse the star. So this balance keeps the star in that state for millions of years, in certain cases even billion of years. And when this internal fuel of the star gets exhausted, obviously the gravitational pull takes over and it collapses the star. A star can collapse into something called a neutron star, which is a very small star, or it can collapse into something which is called singularity, which is a black hole. So Indian scientist Subramaniam Chandrasekhar did a lot of research in this area, and he came up with something called Chandrasekhar limit. If the mass of the star is above this Chandrasekhar limit, then those stars can collapse into a singularity, into this point mass. The entire mass of the star is collapsed into a dimensionless point mass. It doesn't have any volume, and that is called a singularity. It's still a big mystery how this entire mass collapses into a point mass which is of infinite density, and as per Einstein's general theory of relativity, it can create an infinite curvature of space-time, which can create a tremendous gravitational pull which can suck in anything which comes close to the black hole. So around this point mass, around this singularity, there is imaginary boundary of a black hole which is called event horizon. Like the singularity is at the center of the black hole, and it has a boundary called event horizon, and anything which crosses this boundary is going to be eaten away. Even the fastest entity in the universe, light, even if light enters the event horizon, it is going to be sucked in by the black hole. And we cannot see anything inside the black hole. That's why it's called a black hole, because even the light cannot come out to tell us what is happening inside. So we don't know if all this matter which is going to the center of this entity, center of this object, what is happening on the other side? Is it trying to spew another universe on the other side? We don't know what is really happening inside. So this is in brief about the black hole. I'll add something when we'll talk about the black hole for which the image has been taken. I'll add certain things when we come to that. So as I said, the black hole for which the image has been taken is at the center of the M87, the Mathur 87 galaxy. It's a very massive galaxy. It is not just holding all the cosmic objects of that galaxy together, but it is also anchoring the other galaxies in the Virgo cluster. So even our Milky Way, it is helping to even anchor our Milky Way galaxy. So it's a huge galaxy, and because of its gravitational pull, it is helping the other galaxies to stay together. And this galaxy, the size of this galaxy is 120,000 light years across. If you want to travel from one end of this galaxy to the other end of this galaxy, it is like 120,000 light years. So light, also the light, which is the fastest entity, it takes 120,000 years to go from one point of this galaxy to the other point of this galaxy. So you can imagine how huge this galaxy is. And this black hole is also a monster which is there at the center of this galaxy. This black hole is 6.5 billion times the mass of Sun, 6.5 billion times. Just for comparison, actually, I'll talk about the black hole which is there at the center of our own galaxy, Milky Way. It's still a prediction, but mostly it is also going to come true, as it has happened with M87 galaxy. We still have not taken any image of Sagittarius A, which is the black hole at the center of our galaxy. But as per the prediction, as per the estimation, that black hole is 4 million times the size, the mass of Sun, and the black hole which is there at the center of M87 galaxy, it is 6.5 billion times the mass of the Sun. So it is much more massive than the black hole which is there at the center of our galaxy. And then it is very far off, like it is 55 million light years away from us. This M87 black hole is 55 million light years from us. The light takes 55 million years to travel and come to Earth. And the black hole which is there at the center of our galaxy, Sagittarius A, just for comparison, like that is 26,000 light years away. That itself is a big distance, but when we compare it to the M87 black hole, which is 55 million light years away from us, that distance is astronomical compared to the distance which is there from the center of our galaxy, the black hole at the center of our galaxy. So, and the size of the black hole, the M87 black hole, is 40. When I say size, like the event horizon, if you look at this is the event horizon. So if you look at the diameter, this diameter is like 40 billion kilometers, which is like 1.5 light days across. So it looks a very small number, 1.5 light day, but light travels at speed of 3 lakh kilometers per second. Light can circle our Earth 7.5 times in 1 second. Light from Sun reaches to Earth in 8 minutes. So 1 second, 7.5 rounds of Earth, 8 minutes light coming, the photons of the light coming from Sun to Earth, and 1.5 days. So 1.5 days significantly more than 8 minutes. So you can imagine like how large distance it is, 40 billion kilometers. It is so large that it can eat away most part of our solar system. It can eat a big chunk of our solar system. If our solar system obviously comes near the event horizon, it can eat a big chunk of our solar system. So that is about brief about this black hole. This black hole has been given the name of Powehi, P-O-W-E-H-I. That name has been given by a professor at University of Hawaii, Professor Larry Kumira, and it is still, I don't think, the official name, but yes, as it is the first name given to the black hole, I'm sure this name will always remain with this black hole. So you can see an outward ring around Powehi, this black hole. So we talked about the point of singularity, which is there at the center. We talked about this event horizon, which is the imaginary boundary of the black hole. Anything crossing event horizon, as I said, is going to be eaten away. So there's a tremendous amount of gravitational force which is there around this black hole. So the matter which comes near it, the cosmic dust, the gas, all the matter which comes near the black hole, it is going to try to eat it away. It is going to pull that towards the black hole, and this matter which is around it is spinning, or it is swirling around the black hole at a very, very high velocity. It is going around this event horizon at a fraction of speed of light. So this high velocity movement around the black hole is causing a tremendous amount of friction, which is generating a lot of heat. This is a temperature in tune of billions of degrees, and that is causing this luminosity around the black hole. That is causing this brightness, this orange ring around the black hole, and this ring is called the accretion disk. This accretion disk consists of the cosmic dust, all the matter which is moving around the black hole at high velocity. So part of this matter is going to be eaten away by black hole, but we cannot see that because anything entering into the event horizon cannot be seen, because the light is not coming out to tell us anything about what is happening inside the black hole. We can see this orange ring is brighter on this side, and it is brighter on this side, and it is a little faded, or it is less brighter on this side. So what happens is this black hole has been found to be rotating in the clockwise direction. This black hole is rotating in the clockwise direction. So when I say this black hole is also rotating in the clockwise direction, and the accretion disk which is surrounding this black hole, this matter disk which is also revolving at high speed, is also rotating in the clockwise direction. So what happens is, let's take that Earth is here, just to understand the concept. If the Earth is here and the black hole, this accretion disk is rotating in the clockwise direction, this is the part of accretion disk which is basically moving towards the Earth. So the light is going to be brighter from the part of the accretion disk which is moving towards the Earth, and as it goes away from the Earth, as it rotates and it moves away from the Earth, the light coming from the part which is moving away from the Earth, the light is going to be comparatively less brighter. It's going to be comparatively faded compared to this portion when the light is coming towards the Earth from this portion. So it can be explained by just another very common phenomenon which we see in our daily life. Like if a person is standing here and if a car is approaching the person and is honking continuously, then obviously you will hear the sound much more louder when it is approaching you compared to when it is crossed you. The sound intensity will start going down as it moves away from you. That is called the Doppler effect. So the similar thing is happening, like part which is approaching the earth, the light is coming brighter. As it moves away from you, the light becomes comparatively faded. So this orange ring we talked about, then what happens is there is a jet of matter which is also emitted out of this black hole, and also electromagnetic radiation is emitted out of this black hole. This jet of matter which is emitted out runs hundreds and hundreds of light years across in the galaxy. So as I said, this galaxy is 120,000 light years across, but this jet of matter which is emitted out also runs like a few thousand light years across. And the electromagnetic radiation comes in forms of X-rays, in form of radio waves, in form of infra beams. So now we'll come to the part like how we have taken the image of this black hole. The image of the picture of this black hole is taken using the Event Horizon Telescope. Event Horizon Telescope is an international collaboration, and a lot of people from the scientific community have contributed to it. And this telescope is not a single telescope. Well, what was required to take an image of this black hole was an Earth-sized telescope. But as it was not practically feasible to have that size of telescope, so there were 8 telescopes which were stationed, 8 observatories which were created in different parts of our planet. So there are observatories in US, Chile, Mexico, Arizona, Antarctica, Spain, Hawaii, South Pole, and these different observatories are synchronized using atomic clocks. So they are synchronized, they are working in harmony, they are working like an orchestra together, and they are taking image at the same time of the black hole from different angles, and then these images which are taken are correlated later when we feed all this data to the supercomputer to construct a unified image. So as I said, like these images are taken from these different telescopes, and this data is so large, it's trillions and trillions of data at each site. The overall data is 5 petabytes of data. 5 petabytes of data is like millions and billions, millions of billions of data. One of the scientists mentioned that it is like recording MP3 file data for 5,000 years actually. So this is the size of the data, and this 5 petabyte of data cannot be transferred over internet. Internet is still not so evolved, technology is still not so evolved that it can transmit this size of data. So that is why all this data at different sites was collected on the physical drives, and then all these drives, like around 1,000 drives, I think 950 to 1,000 drives, the physical drives were there in total, and then this data was transferred to 2 locations, one to MIT and another to Max Planck Institute of Radio Astronomy at Bonn, Germany. And then this data is, a lot of unwanted data is also there, so it took a lot of time to remove the unwanted data to come up with data what was really required, and then it was correlated, because you need to have the data which is, you should be able to correlate the image taken at the same time from different observatories. So all this data was correlated after filtering out the unwanted data, and a unified image was created on these supercomputers using complex algorithms. And you must have, I don't know if it's been seen in the news or not, but yes, there is a lot of news running which is featuring Katie Bowman. Katie is one of the lead software programmers or research scientist who has written this algorithm for creating this unified image of a black hole. So one important thing I would like to mention is not that we are getting direct images of the black holes. Basically, we are getting the radio waves. We are getting it in form of radio waves, and then from these radio waves actually the image has been constructed. So it's not a direct image, but using these radio waves, and after correlating all these radio waves, data from all these radio waves, the image is being constructed. So as I said, like Katie Bowman and Andrew Chall and Honma and other, there are a few names which are doing the rounds in news. I'm sure there are a lot of other people who have contributed to the algorithm and software part also. But I think Katie is one of the key contributors and is a spokesperson. So have seen her in the news talking about this amazing thing which has happened, the first ever picture taken of a black hole. So I would like to mention that the black holes were predicted by Einstein's general theory of relativity. Einstein had predicted these dark objects covered by a ring of light, and that has come to a reality now. So far it has been a hypothesis or a prediction, and as I said, like even Subramaniam Chandrasekhar talked about it. Obviously he did not call it black hole. The black hole name was given much later by John Wheeler in 1969, but Subramaniam Chandrasekhar did talk about the concept, and even Schwarzschild talked about, Schwarzschild also talked about it, and initially Einstein himself was not very sure about what his theory and his equations were predicting, but then Schwarzschild also contributed to it, and later Einstein was also convinced that yes, such an object exists in the universe, and that prediction has come true. So far the simulations and the science fiction, we have seen the images of black hole, and that matches very much to the actual images, actual pictures that have been taken of the black hole, M87 black hole, Powehi. Powehi, the name I talked about, given by Larry Kimura, professor at Hawaii University. The Powehi name means embellished dark source of unending creation. So embellished dark source of unending creation, and that is the meaning of word Powehi. And we may see new names coming about these black holes from scientific community also in future. Now this Event Horizon telescope, which is taking these images, is also trying to take images of Sagittarius A, the black hole at the center of our galaxy. Let's see when we get the images of it. And the EHT project is also trying to expand the number of telescopes from 8 to 11 or 12 by 2020. They are also trying to put telescopes in space so that they can get higher resolution images of the black hole, which can give us more information about the black hole in future. The interesting thing is the black hole, as I talked about, this point of singularity which is there at the center, it is point mass, infinite density, and that cannot be explained by the laws of physics which we understand today. So either new physics is required to understand that, or from the data that we have collected, that may give us some hints to understand like what is really happening in the black hole, because nothing is coming out to tell us the information about it. But from whatever data has been collected, I just hope that scientific community comes to know more about the black holes and more about laws of physics which we may not be knowing at this point of time. So definitely it is not any mean feat. It is a big achievement, but I would say it is still the beginning. We may get more and more images and more data about the black holes in future, which will help us to understand more about these mesmerizing astronomical phenomenon, which is definitely catching fancy of all the people, not just of the scientific community, but of general public also. Thank you.